One of the features of state trees is the ability to create evaluators. And these are fundamentally different in concept to tasks, especially global tasks, even though you may use the two interchangeably. The purpose of evaluators is to gather data and to evaluate conditions that can then be used by the state tree or by state tree tasks to make decisions and trigger transitions. In other words, it provides the data that the state tree may need to evaluate its logic, but it does not trigger the actual transitions itself. The types of things you would use evaluators for are for setting references to objects in the world, like the player character or player controller, calculating the distance between one actor and another, or running line traces and providing the hit results for a task to act on. This type of code should be put in your evaluators as a way of separating the gathering of data and computing variables from the action of acting on them in tasks or state tree conditions. Evaluators are part of the asset details of the state tree, and in state trees, order matters. So an evaluator will have access to any data that comes above it, from the context actor to the parameters, and anything that comes after the evaluator, the global tasks, or the entire state tree itself, will have access to its data, which it makes visible. The evaluators that you create will start running when the state tree starts, and they will continue running until the state tree ends, and they will run independent of the actual states themselves. You can add an evaluator by simply pressing on the plus button here, and you can add as many evaluators as you require. The way that you create an evaluator is slightly different, as you do not have access to a menu item in the actual state tree editor. And this is probably because evaluators are less commonly created than global tasks. Before we create our first evaluator, let's look at our state tree and see where we are going wrong. At the moment, our state tree operates by calculating a distance between the player and the actual door. And we do that in our state tree task, player check player distance. However, we are getting the reference to our player in the task itself and performing a distance check in order to evaluate a condition. And this is the exact type of action that should be done in a evaluator instead of a task. So if we go back to our state tree itself, what we will need to do is create an evaluator that will get player data for us. So we can go to our content drawer, we can right click, go to blueprint class, and we'll need to type in evaluator. And this will give us access to the state tree evaluator blueprint base, which is the base class for creating state tree evaluators in blueprints. We can select that, and we can call this state tree evaluator, should we say, for player door data. And we can open that. The evaluator blueprint looks similar to a state tree task blueprint, in that it is completely empty when you open it up. And if you go to the class settings, much as we saw in the task blueprint, you can set a display name for it. So we could say this is player evaluation, as opposed to, say, world evaluation. We can give it a category, maybe say this is for player, and those names will show up in the menus when we add evaluators. In the class defaults, it is slightly different in that you can set a description, and you can also give an icon name and an icon color. And this will change how the node appears as a name. So if we wanted a different name for the node in the actual editor itself, we could just call that player. And if we compile and go to our state tree again, when we go to add our new evaluator and the category player, we get the blueprint name player evaluation. But under the evaluators, we get the description name of just player. There is an option to set an icon name, and if we hover over this, it gives us one example, which we can just enter. And then if we go back to our tree after compiling, you'll get a little icon here. And there are probably other options available, but there's little documentation, and I suspect you have to go to C++ and use Slate to create your own. But we'll leave that for this particular video. Just like state tree tasks, you also have access to variables. So this is where you would maybe set your door reference, set it as an actor, and the same category options that we saw in state tree tasks are available here. So if you set it as context and compile, it should automatically have a binding to the context actor, as we can see by that icon again. And the other category names like input and output would also work. So in our case, we want to calculate a distance and then provide that information to the state tree. So if we go back to our evaluator, we would add a variable, which would be distance. We would set that as a float, and then we would set this as being an output, which tells the state tree that we will be providing the result. We can compile, and again, when you use the correct category names, you don't need to make it visible. So that should then show up as a distance out float, and we can set about calculating that value. Just like in state tree task blueprints, there are override functions available in the state tree evaluator blueprint, and this is where you will hook in the execution of your logic. And the override functions available here are slightly different. So whereas in the state tree tasks you had enter state, completed state, tick state, and exit state, the state tree evaluator has as its main entry point the tree start, and this is called when the tree begins. And at the end, when the tree is finished, it calls tree stop. And while the tree is active, it will tick within event tick being called. And as opposed to state tree tasks, which have a finish task node, state tree evaluators have no concept of ending. So they begin and then they run continuously from beginning to the end of the tree. So there is no finish task equivalent. And the way to think of it is that you will use the tree start to set up your references or to bind to any event dispatchers. You will then execute your logic either on a tick or on a timer. And at the end, on the tree stop, you will do any cleanup that is needed, like unbinding from an event dispatcher or setting changes back to their default. The tree start is usually where we will begin. And we want our evaluator to continuously update the distance between the door and the player character. So we can create a function that does this, calculate distance to player. And we can set about doing that calculation. So we'll need a reference to our door actor. We could change this to our schema door, so BP door, just to make it consistent, but there is no absolute need to do that. Now we can take our door reference, we can say get distance to, and the distance is to our player character. We can then set that as our output variable called distance. And if we want to continuously update this variable, we would most likely override the tick function, or we could set up a timer. And on the tick function, we would just call our function calculate distance. So the event tree start is optional, like all of the override functions available to us. But this is a place where you may want to set up your references. So say, for instance, our door is on a ship, and we want to expose a reference to our ship or to bind to a event dispatcher it may issue, like we are going into red alert. This is where we would do it. So we could get an actor of class, and I've just created a default spaceship class, and we could promote that to a variable, call that our spaceship reference. So this would then be available if we set this as an output to our state tree. We could also bind to its event dispatchers. So we could say bind to event red alert, which is an event dispatcher I've created in that actor. And we could create a custom event that just says red alert activated. And when this red alert is activated, we might want to set a red alert value as a Boolean in our state tree. So we could set that as red alert. Again, this might be something that our state tree wants to use to evaluate itself. So we could set that as an output and say red alert true. The tree stop is where we would clean up this binding. And the tree stop would be called if we explicitly stop the tree, or if the component the state tree asset is on has been destroyed, or if the actor has been destroyed. But that might be a place where you would do some cleanup. So for instance, in our case, we might say on tree stop, we would get a reference to the spaceship, make sure that it was still valid, and then we would unbind event from red alert, which would be this event there, and that would clean up any bindings, or create an event just to make it cleaner. But what you notice is that in the evaluator we are setting data, but we are not triggering any transitions, and that is the key concept of the evaluator. So all of this data would then be available to the state tree for it to decide what to do with it. So if we go back to our state trees and now just look to see what it looks like. So we've got references and we've got outputs that are coming through. Now the one thing we know we want to do is we want to replace this calculation with the result that we are getting from the actual evaluator. So we could create a variable in our state tree task, which is called distance to player. Set that as a float. We can compile that. And in this case, we want this distance value to be set by the state tree explicitly. So we would set its category as input. This tells us that the state tree will give us this value. And then we can take this distance to player here, and we can just replace it on this task. So we don't need to do the calculation. That is done in an evaluator. We just simply need to decide based on a threshold distance whether to make any changes or trigger transitions. Then in our sci-fi door state tree, we find where we are using this. So door closed is using that task. Trigger transition based on distance. When we open up our task, we can now see that distance to player is set as an input, and it's a float. So we want to bind it to this distance out. So if we go across here, where our options are to bind, we go to our player evaluation, which is our evaluator, and we bind it to distance. And then we can make a decision of what the threshold distance it is comparing to. And the other place where we have this is on our should close door. So trigger transition based on distance. Again, we will set it to the evaluator's evaluated distance. Compile and save. Our state tree should still work as expected. So if we go back to the editor, we play, again it's closed, we go close to it, it opens, open, we move away, it closes. So again, the variable is being computed for the correct distance. But this time, instead of it happening in the state tree task, we are doing it in the actual evaluator. And then we are sending that information back to the state tree for it to make a decision on what to do. Evaluators can also be good places to get line trace data. So for instance, we want our door only to open when the player is looking at the door and within a certain distance. So I've created a line trace function called isPlayerLookingAtDoor, which will set a Boolean player looking at door. We can then call that on tick, again if we want to, or we could do it on a timer. But that will set a player looking at door as an output value. We could then in our check player distance not only check to see if the player is within the required distance, but also do an AND Boolean, check to see if the player is looking at the door. Looking at door as a Boolean, and again we want this to be set explicitly, so we'll put that as an input. And we can then put that as our AND, and this will be our Boolean check. Back in our state tree, again, this will come out as an output for us. We can then go to our task, and we can find our looking at door as an input. And as we showed in the previous videos, the advantage is we will get errors if we do not set it in the correct task. So that can help you with preventing problems from happening. So looking at door, we can go to the Boolean, player evaluator, and put player looking at door. So that will decide whether we can open the door. We go to our close door, and that was here, check if should close door. Again, we can open that trigger transition task, go to the looking at door. Perhaps this time we want it to be the opposite. So when we're not looking at the door and we're a certain distance away, it will close. So we can go to the logic and we can actually say a not. And the input value here that we're going to not it will be player evaluation, player looking at door. Now when we compile, it should compile fine. We can now go back to our editor and test it out. When we play, now the door should only open when we are within the correct distance and looking at it. So we're in the correct distance but not looking at it, so it won't open. When we start to look at it, it will then open. And when we move away a particular distance, again, and are not looking at it, it will close. And for as long as we are looking at it and in the correct distance, it will open. And then when we walk away, it won't. The main thing being that when we are just walking sideways across it, it will not open until we actually look at it. So our evaluator is providing the correct data, and our state tree is utilizing that data to make decisions on its transitions. But one thing to be aware of when you do line traces in evaluators or tasks is that the self, which is ticked by default, in this particular case actually represents the actor, and that is the actor that we are checking for as a hit actor. So make sure that that is unticked. And again, sometimes ticking trace complex on or off may be helpful depending on your static mesh or skeletal mesh. So the key thing to remember about evaluators is that they gather the data and compute the variables that will then be used by the state tree or its tasks to make decisions and trigger transitions. And you can create as many evaluators as you like in order to categorize them depending on the type of work that they will perform. One of the visual advantages of using evaluators is that you get to see all the data that will be available in your state tree. And that can then determine how you create your tasks or set up conditions on your state tree. As long as you are computing simple values on your tick functions, there should be no major performance impact. But that is something just to be aware of. And there are ways, obviously, using timers or other means to reduce the frequency by which you are performing these computations. But I hope this explains the concept of evaluators how to use them, where to use them, and what their purpose is in state tree logic.